Wow, everybody, thank you for coming. This is very touching. Frankly, nice to see everyone. So, we've been working on the notion of limit at infinity. So, function from the reals to the reals, or a subset of the reals to the reals, has a finite limit at infinity equal to L if for all positive epsilon, and epsilon is our level of precision, we can go far enough out on the x-axis so that beyond that point, the function stays within levels of precision. That's what epsilon is. It's how tight is your balance. That's what was level of precision. It's a great definition, and we'll be working with it in other cases. It helps make continuity much cleaner, these types of definitions, so we can get a lot out of this. Mostly if you try to do limits by inspection, much quicker, much easier, and we like to do that. Not all functions have finite limits, but you could have an infinite limit. So if you just had something really simple like f of x equals x, as x goes to infinity, well, the function goes to infinity because it's equal to x. And so you would say it has an unbounded limit, and it should be infinity. So you can do that same thing for other functions. And the key there is you give me any finite bound. Within any finite bound, no matter how big. I realize that doesn't look super big on the chart, but imagine the scale is 10 to the 500 there. Then if I go out far enough, the function stays above that bound, never cross below. So that's the notion of an infinite limit. And then there's functions that just kind of wiggle around, like sinusoids. They don't settle down to anything. So the notion of limit is settling down, or exploding and going away. And it can explode negatively as well. So that's the notion of limits. When you have a rational function, life is sweet. So you just factor out the highest terms in your polynomial in the numerator and the denominator, because they dominate all of the other terms as x is getting large. And so the limit of that complicated function is really the same as the limit of bm over an times x to the m over x to the n. And then you just have to look at this x to the m over x to the n. Once you cancel all the stuff, you have an x in the numerator, or powers, or do you have powers of x in the denominator? You removed everything in the numerator, or m and n are equal. So if m and n are equal, that cancels, and the limit is just bm over an. Yes, m is greater than x, so you end up with leftover stuff after you cancel n of that out. Then it depends on the sign of the fraction bm over an. If it's negative, then the limit is minus infinity. If it's positive, the limit is plus infinity. But if the denominator dominates, then the limit is 0. So basically, if you understand the limit of x and 1 over x, you can extrapolate to get all of the others. The next case that's really simple is when you throw in exponentials. So these are a base number, and you raise that to a power x. And then you can mix them in with monomials, rational functions, etc. Once you understand them, all right, what's going on with monomials, you can extend it. And so here the key thing is, if a is bigger than 1, then it grows much faster than any monomial. So even if a is 1.0001 and m is 200,000, the limit as x goes to infinity is still infinity. And if you have a less than 1, it decreases faster than any monomial can grow. So no matter how big m is, if a is 0.9998, 1 or something, so strictly less than 1, then as x gets big enough, it crushes the monomial. So you can do all of those by instead. That works? Yeah, 1, 2. We just got started a little bit on things called indeterminate forms. So infinity is a concept, it's not a number, but yet we can still do a few algebraic things with it. We talked about in lecture that if you have 2 and you add infinity to it, it's still infinity. Okay, so you can add finite numbers to infinity and get infinity. You take a finite number, subtract infinity from it, and you get minus infinity. So those things work. It's when you have infinity minus infinity that you can get into trouble because it can equal anything. Now here are the key examples. If you look at the first one, you have x minus x squared. Well, the x squared is going to dominate. So as you let x go to infinity, you're going to get minus infinity. But if you were naive and evaluated the limit term by term, you would have infinity minus infinity, and you would say 0? Okay, that is not true. Okay, so you cannot say 0. The middle one, the x cubed over x squared, well, the x cubed dominates. The x cubed dominates, yes. And so if you did it term by term, you once again have infinity minus infinity. But if you put that over a common denominator, the x cubes cancel, and you end up with the limit being 0. And then finally, x squared minus x is just the negative of the top one, and you get plus infinity when x grows. So things where the relative growth rates determine what's going on, that's called indeterminate forms. And infinity minus infinity, it depends on the specific cases. And there's a video link that we'll use later. I just stuck it into the notes. So today we're going to continue with our algebra limits and how we can do sums of limits, ratios of limits, and a few other things like that. Okay, so we'll get started. So I like to call results like this, calculus is not evil. And what it says is, if you're dealing with functions that have finite limits, the limits of the sum is the sum of the limits. Limit x goes to infinity, f sub I of x is finite. So it exists as a finite number. Then all real coefficients. So limit of a sum, which that x of what right alpha f5 x is equal to the sum of the limits. The limit of a sum is equal to the sum of the limits. And I actually like simple results like that. Once you get is what as often as possible to break down very complicated limits to simpler. Okay. There. Now I'm more looking at you. I feel better. I don't know what you're doing. Throw this example. Check the limit. That's goes infinity. That'll make an awkward sum here. Some of this is just way to address it to try to confuse unaware observer. No one in this room is going to fall into that category. Okay, so if we were to use our results on rational functions to solve this problem, we would be obliged to grind it over a common denominator. Because we know how to take limits of things that are relatively simple, so the ratio to polynomials and exponentials. But with this other result in our back pocket, if each of these limits is finite, then we can just add up the results and get the overall limit. So what is the limit of this first term? It's got a square in the numerator and a cube in the denominator.
Sure.
Everybody agree it's 0? Okay. Patently obvious to you that it's 0. What about this next one if I don't guide your thinking?
Great.
It's 3, because we have 3x squared divided by x squared, so the two degrees are equal. And so we got 3 divided by 1 is 3, and that's so it's equal to 0 plus 3 equals 30. And the key thing is did not have place over a common denominator. That would have been really what it's solving. In fact, okay, so results like this, I know they look kind of formal. Oops, I left out my alpha I, so I'll put them in red. My bad. Results like this that are formal allow us to take situations that are somewhat complicated and turn them into really easy by inspection. But so that's the purpose. Okay. So you guys got that easily. Let's do some more intuition. Suppose I have a positive constant.
Correct.
And I multiply it by infinity. What should I get? Anybody online on a touch yet?
Thank you.
Okay, because the constant is positive, we're going to get plus infinity. Alpha is negative. Check.
Yeah.
We'll write this in red. However, 0 times infinity is undefined. And there's another of our indeterminate forms. Indeterminate.
That's them.
So cannot be determinate without analyzing the specific case. Okay, so why is it indeterminate? Why do we have to be careful when we see limits like that? Oh, I'm going to build examples that are very analogous to how when we had infinity minus infinity, we can get anything. It's possible. Okay, so let x get really large. I'm going to put in two terms, and we'll look at the individual terms. Right, so if we're just looking at this first thing and doing the limit naively term by term, that's 0. And if we're just looking at it naively, taking the limit inside and evaluating that one, that's infinity. However, the correct limit is we have a fourth power in the numerator, a second power in the denominator, so that numerator wins. And the answer is infinity. We'll do nothing. So I'm going to keep my 1 over x squared plus 1. But this time, set the other power.
Good.
Again, when x gets large, the ratio here goes to 0. When x gets large, if we naively reach in and do the individual limits, and then we're multiplying 0 times infinity. But the problem is, in reality, we see we have x squared in the numerator, x squared in the denominator. The leading coefficient in each case is 1, and 1 over 1 is 1. So the answer is 1. Now, finally, limit x goes to infinity. Keep the first term. Just the second term again. So you guys are, yeah, I get it. Each of them are going to be 0 times infinity. That's his game today in this part of the lecture. And so we have 0 times infinity, but what's the real answer? Well, there's a first power in the numerator, a second power in the denominator. So the denominator dominates and crushes the numerator. And so this time it's 0. And you can get any other number you want. You can get minus infinity, etc. Okay, so 0 times infinity is an indeterminate form. And similarly, 0 over 0 and infinity over infinity are also indeterminate forms. Okay, so we're going to go through limits in a careful enough way that we know not to fall into these traps. And the thing is, calculus is just full of these limits, and if you understand them intuitively, where you can just analyze them quickly and you know the bad cases, it all becomes transparent. So we're going to try to get to the point where it becomes transparent for us. Okay, so here's another simplifying trick or result. But once again, calculus is not evil if you set yourself up properly. So I suppose we have a function taking 0 infinity to r. We have a second function that does the same thing. And so let these be two functions. Suppose that the limit of one of them exists and is finite and is non-zero. So we're just going to choose sheep. What is the limit? X goes to infinity of g of x.
You tell me.
The ultimate highlight its beautiful characteristic. The limit exists. It's finite. And non-zero.
Yep.
Why non-zero? Because we don't want to fall into this trap of 0 times infinity, 0 over 0. Infinity over infinity can be rewritten as 0 over 0 by pounds.
Yep.
One of them is nice. The other function we don't really
I want it.
worry too much about.
Two.
Then
So,
the limit of the product is the product.
that's a yes. Two. It's a kind of.
Okay, so we've written this in a pretty general form because g of x is not 0. So f of x, its limit could be finite, it could be infinite, it could be undefined, and the result is still the same. Okay? So this is this people online and see, so if this is 3, and this limit is, if this turns out to be the limit of something like sine of x, which is undefined, then the whole thing is undefined. And you get to break it down. If f is like x squared and is going to infinity, that's okay, as long as this thing is finite and we're not trying to multiply by 0. So that non-zero hypothesis means that we don't have to make any hypotheses on how the limit of f is. If we have a product, we can break it down into where one of them has a finite limit, then we can take care of the other one. So it's a divide and conquer strategy. Divide and conquer. Engineers strive to divide and conquer. Two ratios work out the same way. Limit x goes to infinity. F of x over g of x equals the ratio of the limits.
It should be.
Okay, so we've got a complicated function as a product or a ratio. You know, maybe you can just analyze it, and if the top one's f is a polynomial, g is a polynomial, or we got some exponentials in there, great. But if it's a little more complicated, we are given the possibility of breaking the function up and doing individual limits, and then just doing algebra of numbers.
Check.
So that's the whole idea.
Please. Yes.
Let's do this first one. Of course, it's chosen to be as gnarly as possible.
I can. Steve. Ah. Worst. Stick box there, sorry. That's fine.
Okay, so
Down. Pitching.
this term 0. This term 3 over 1 is 3. So we can get that as 0 times 3 equals 0. With we've got one limit.
I'm choosing the right to aware.
With f of x is equal to x squared minus x to 4. G of x equals 3x squared over 7 x squared minus 6x plus 11. Okay, so here we go. Well, not so bad because it's just polynomials, and we could have multiplied it out, and we'd have seen that the top degree is 5, the bottom degree multiplied out is 6. The coefficient times that one in this problem is not too bad. It'd be -1, but because we have 5 over 6, we don't care about the coefficient, and we would get 0. So we could do it with our teacher to get problem other way, but it's also a little bit simpler not to have to do that. And so let's try this one. Okay. So what is the answer here now? I'll let you work on it. So if it has a finite limit, give it to me. If it's undefined, say it's undefined. And if it's unbounded, let me know it's unbounded. Give you a minute to break it up, however you want to do it. So you see sine of x, if you're a little bit suspicious that something not going to work here, right? The sine of x is going to about settle out. That's the intuition. You need to have intuition at least. Because, well, before we do an answer, like we do f of x is x times sine of x. And we let x goes to infinity. This is undefined. Okay, because that's just going to I'm not very good at my drawing, but you guys get the idea that it doesn't settle out. And then if we let g of x is 1 plus e to the minus x plus e to the minus 2x, as x goes to infinity, that goes to 1, so it's not equal to 0. And so we can conclude that the limit is undefined. Is that how you solved it? Maybe? Okay.
I'm pitching it.
we made a different choice. F of x equals
I be
sine of x. And so x is two. That's just fine. And g of x, we keep the x and we put all these other nice exponential terms that we understand. Okay, if we try to decompose it like this, our result does not apply. Infinity times undefined, and we don't know what the answer is. So remember, our hypotheses were one of the functions has a finite limit that is not zero, and we don't have that in either of these cases. And the moral of the story is if madness anything wise, one can make good and bad choices. How about that for more? On a Wednesday afternoon, okay? Think you could use that line at a cocktail party this weekend and help impress some friends and stuff like that? Any chance? And math has a lot about it. But anyway, I use these little over-the-top things just to try to help trigger a neuron where something will actually stick, okay? That's all I'm trying to do, is that we have a theorem, a proposition here, and for us to use it, we need to verify that all of the conditions are actually satisfied. And one of our conditions was we have one of the functions when it's chosen is nice, and it has a limit that is finite, but it's not equal to zero. And this one, with the second choice, we did not have a finite limit. We had a limit, that was nice. We had one that was undefined. And if this had been 5 or 1 or whatever, like we had up above, then finite times undefined is still undefined, or finite times infinity is still infinity. But 0 times those is meaningless. So it's very, very easy to write down stuff in calculus. That's just nonsense. Yes, we're trying to get our nonsense filters built up a little bit. Questions on that? Think you can apply it? You can check the hypotheses and just be a little bit careful with it all does. And what it allows you to do is decompose what looks like a hard problem into something that's easier. Okay. Start slightly different direction. Move into what's called geometric sums. So, definition. A real number and R a real number.
I don't know.
S sub n by definition equal to A
Like
space times R space times R squared A times R to the n. Here I'm changing the definition. I'm just going to write it down. The sum Let's note that this all works out because when we've got 0 here, this is 1, and that takes the first term. When I is 1, that's the second term. I is 10. That's all that stuff. That's all that stuff works out. That's it's called the geometric sum. Then I'm took R is bound with the bridge.
So. 1. 2.
Okay, what's the common ratio thing? If you take term and you divide it by its preceding term, you just get R. So here you would divide by A, R to the n minus 1, and you just get R. Here you divide by A, you just get R. So that's what it's called. It's the common ratio. So each term, you just add in the previous term times R. What do they look like in real life?
Check.
Well, picture you. 2 bottom plus a half plus quarter plus 1 over 2 to the n. This is bullet. Okay. Can we recognize A and R? Just first term is A. So A equals 1. And then we take the second term and divide it by the first term, and we get R. So half divided by 1, we get R. So R. And then this is also a big thing. Yes. That's not too bad. So if I have 2 6 plus GT, that's dot, and I don't write down which I will turn it for you. I'll come back and put something here. But just from this data and assuming that it's a geometric sum, we recognize the first term is A, and then 6 divided by the first term gives us R. And then look, if we do the third term, 18, and we divide by the previous term, we get R as well. Okay, so it really is. So this is 2 times to the n, because it's A R to the n. A R to the n. Figure it out. So for this to be a geometric sum, that's what we're going with. Just a pattern. It's just pattern matching. Okay. Proposition. But R not equal to 1. And so word solution to this S to the n is A times 1 minus R to the n plus 1 over 1 minus R. and if the magnitude of r is strictly less than r, then limit once n goes to infinity of s to the n is equal to state equals minus r. H. Okay, we're going to look at a visual proof of this first so that we can decide if we want to do another proof by induction or we don't want to do another proof by induction. I'm flexible on that. But let's know this. This is the only part that depends upon n when we take our limit if that goes to infinity. If this is less than 1, we're in the case of an exponential with the base that's smaller than 1. Hence, that decays very quickly to 0. So we're left with a times 1 over 1 minus r. So that's where that comes from. Called see a better principles. I think. Okay. Try. Or done. Okay, it's not the general case, but the whole series of videos here. So let's just stop. What do we have here? Because it goes pretty fast. We have a triangle that's been broken up into 1, 2, 3, 4 equal parts. So this is 1/4 of the area of the triangles. Everybody agree? Okay. Now, this breaking it up into 4, we can do here. And then we can do that again. And that's called what? Induction. Okay? That's all induction is. Okay? Just repeating the process over and over. So let's do it. And quarter squared. Here. Well, okay. At each level, this area is 1/3 of the total area here. Okay. At the next level, this is 1/3 of the total area at this level. And that pattern holds true at every level, correct? So if you add up all of the middle sections, how much of the area of the triangle do you get? 1/3 of it, okay? Isn't that beautiful? Okay, so that's what it's going to do, okay? Now I'm going to rearrange things, and you can say, I don't know that I believe the rearrangement, or you can say, I believe the rearrangement. No, was that just trickery or something? No, look at it at each level. See exactly. That's how geometric sums work. Okay, so is that that's more entertaining than writing out the symbol to proof by induction, right? For sure. Now, is it more satisfying or less satisfying? I think that's a personality test, okay? We could have Rorschach tests to just find out all the weirdos in the room. If we start with me, okay, Max is a grad student, so he's pretty weird too. Well, that's a very few let's do that. That's, you're just weird. It's like, I think you're very weird. And you guys are hanging out with weirdos, so you're pretty weird too. Okay, so we'd all fail the test, but would you believe the result on geometric sums based upon these types of animations, or would you rather see the proof by induction?
This.
Like this one.
It sounds like you want to show us why induction.
Yeah, I'm going to put it in, and so you can look at it tomorrow night or never paste it in. But I mean, it just, yeah. You know, when I was a student, guess how often we could do proofs like that one? Yeah, but all those things are available, so you can bring some of these things alive, okay? I think it's fun, I'll be honest with you. Okay.
How? Well,
Let's go back to where we were working on geometric sums, and then all I'll do here is paste it in, and then we'll do a different proof. Because this one, for you guys, is solid enough, okay? Second part here.
and
And it's in the textbook as well, but sometimes when you're just looking through the notes, you go, why is that work? Now, by having it in here, I can do one thing though, which was to remind you how proofs by induction work, is that we have a hypothesis of something indexed by the counting numbers, 1, 2, 3, 4, 5, 6, 7. And we can do the same method we did when we doing the sum of the integers from 1 to n, proving it equals to n times n plus 1 over 2. We define the left-hand side, we define the right-hand side, and our hypothesis is that the left-hand side equals right-hand side for all n. So then you do the base case, just do the calculation, then you're going to ask yourself, does the induction hypothesis work? So if it's true at step k, does that imply true at step k plus 1? And that's what's done here. Okay, so we're not doing the details, we're just reminding ourselves what is the process of a proof by induction. So now what I'm going to do is switch time to, now it's 5:20. So tell you what, I'm going to write down this problem, and those who want to start working on it during the break can, but we'll have extra time after the break to continue, and then we'll see if you guys can do this induction thing on a problem that is nearly identical to problem 3 or 4. I suggest it's almost identical. The numbers have been changed to protect register or something, and here's the problem.
they can't do play.
Proof by induction. And I'm not trying to turn you into mathematicians, all that kind of stuff, but still, we want to be able to read math just like we can read English, French, Italian, Spanish, and such. If proof the sum I equals 1 to n, 2 to the power I, plus equal to 2 times 2 to the n, and minus 1.
That it's true.
So we'll take a break, and I'll give you a couple extra minutes, so we'll restart the lecture at 5:30. So you've got 5 minutes for break, and then 5 minutes to start working on this problem.
So out of curiosity, how many of you have had EECS 203? 2, yeah. Okay, so now we've got weirdos and super weirdos. How about that? Yeah, well, yeah, so after these first few weeks, we do derivation so that you can see the source of a formula, but we don't do formal proofs after this. But this is just getting our foundations of calculus super solid. That's all it is. Okay, so L of m, yeah, L stands for left side, so I'm guessing all of us are good with this. The right side, R stands for the right side. We're good with that. And our formal hypothesis for each n is at L of n equals R of n for all n greater than or equal to 1. Okay, base case. K equals 1, or n equals 1, doesn't matter. Let's just call it n equals 1. L of 1, that's the sum from 1 to 1 of 2 to the 1. Okay, so it's 2 to the 1, which equals 2. R of 1, 2 times 2 to the 1 minus 1, which is 2 times 1, which equals 2. Wow, okay, not very hard numbers. So the base case holds. Remember, if the base case fails, you're done, okay? And it's sometimes called the induction hypothesis, sometimes called the induction step. And the question is, L of k equals R of k implies, and we don't know, so come on, equals implies L of k plus 1 equals, okay, so, and the way I like to say it is, let's find out. Okay, so let's look at what R of k plus 1 is. So that means we plug in k plus 1 for n. And we get 2 times 2 to the k plus 1 minus 1. Okay. And then L of k plus 1. Well, L is the sum, 2 to the I equals 1 to the n, so we set n equals k plus 1. And the only thing I'm going to do is break this up into the sum I equals 1 to k of 2 to the I plus 2 to the k plus 1. And why do I do that? because this is L of k. So it's the same thing we did when we did the sum of the integers from 1 to n, or 1 to k. Then did k plus 1, we recognized, oh, we have a hypothesis about the relation between L of k and R of k. So by the induction hypothesis, L of k equals R of k, and that is 2 times 2 to the k minus 1. Okay, so then it's now plug and chug. We've done all of the thought work. So L of k by the induction hypothesis is 2 times 2 to the k minus 1. This is L of k equals R of k. And then plus 2 to the k plus 1. And as I've said multiple times, you guys are getting tired of it, but the hard part of calculus is the algebra. So what we have here is, what do I want to do? Oh yeah, I want to break up this 2 to the k plus 1 like this, 2 times 2 to the k. That's a valid algebraic step. Now I can factor out the 2 that's common to these, and I get 2 to the k minus 1 here. Whoops, 2 to the k. Come on, Grizzle, that's a superscript, minus 1, and then plus 2. And so that's 2 to the k. So it's 2 to the k plus 2 to the k minus 1. Just doing every step. In your homework, you can be a little bit more concise if you want. And 2 to the k plus 2 to the k is 2 times 2 to the k, which is 2 to the k plus 1. And so we did it. And so we get to conclude that that we have a closed form solution for the sum of 2 to power I, sum I equals 1 to n. Okay, so once you have this, the rest is algebra. Yes, that's the hard part. Okay, because we've got a pattern for induction proofs. Does P of k imply P of k plus 1? And in a lot of these, it's easier to write it down as a left-hand side and a right-hand side so that you can manipulate things clearly. That's probably not how they do the proofs in 203, but I think it's an easier way to look at these, okay? So your homework is very similar. So when you get to the proof and you say, oh, I'm struggling, come take a look at this. So would you like to do more practice on induction, or you've had enough practice on induction? I want more practice. I'm done. So how are you guys going to vote? More. You want more? I thought you were done. One more? 10 more? Okay, so I've got one that's kind of number theoretic, and I've got one that's linear algebra. So we'll do it like Jeopardy. Do you want to do linear algebra for 30 or number theory for 20?
Gotta go for the 30 points.
The daily double. You got it. We've already did that. That was the video, daily double. We already did that. That was the proof. So, but you're right. Okay, so let's do the linear algebra one because it'll remind you of something, and everything we need will just be contained in the definition and the thing. So let's just recall what linear independence is. A set of vectors v1 to vk in Rn is linearly independent if the only solution to the equation C1 V1 plus C2 V2 plus CK VK equals 0, and that's the n by 1 vector in R, it's an n vector in Rn, so it's a column vector, okay? So it's a 0 in Rn, not the 0 in R, is the trivial solution. And that is C1 equals C2 equal ... equals CK. And that's the 0 in the real numbers. Otherwise, the set is dependent. You can say linearly dependent, to be more precise, but it's dependent, okay? So the vectors are dependent. Rings a bell somewhere from Rob 101 or Math 214 or something? Okay, so you've got that definition, and proposition that V1, V2, Vk be linearly independent. If this set X, V1, V2, Vk is linearly dependent, then there exist unique coefficients alpha 1, alpha 2, alpha k in R such that X equals alpha 1 V1, alpha 2 V2, alpha k Vk. Okay. Okay, so you start out with independent vectors. You throw in one more vector, we called it x. It becomes dependent. Then I can write x as a linear combination of the other vectors, and the coefficients are unique. There's not two ways to write it. Okay? Sound familiar from linear algebra? Doesn't really matter, okay? What I want you to do, just talk amongst yourselves for a couple minutes and come up with a proof strategy. And you have everything you need. You have the definitions, so you know what it means to be dependent, you know what it means to be independent. Give me a strategy for proving that I can write x as a linear combination of the first set of vectors, and then, you know, once you have that, getting uniqueness will be straightforward. So that's what I want you to do. And if the way you work together is doing me, myself, and I, that's fine too. We're all, we can all be our own individuals. That means I want help, or that means I'm tired and I'm stretching. Yeah, I hear you. Everybody got an opening move in mind? We're just practicing logic here, and then we're going to move on to other things, okay? It's just I'm trying to abate your fear of formalism. Okay? It's just a very compact, precise language, and that's all we want it to be. Okay. Anybody want to give me an opening move? Pawn to e4 or something, okay? We're going to move the knight, chump the pawns, and move it up to the third rank. Okay, what's the first piece of information we're given? That we have a set that's linearly dependent. So that's the thing we're given. Everything else is really just definitions, okay? X, V1, VK, dependent, implies there exists, I'm just applying the definition of dependence, there exist coefficients C0 up to CK, not all zero. So there's a non-trivial solution to the equation. Such that C0 times X plus C1 times V plus C2 times V2 plus dot, 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 CK times VK is equal to 0 in Rn. Okay, so that's the definition of linear dependence. Okay, I claim from that everything just kind of falls apart. Okay, so you've okay, you're playing what is it, Jenga, and you ripped out the bottom boards and the whole thing just tumbles. Okay, why is that? Let's talk about it, then I'll write down a few things, and what I'll do is I'll just put the whole proof in later before I post it. Okay, so they're not all zero. Can C0 be zero? So one of them is non-zero. Can C0 be zero? If this is not here, okay, so if C0 is zero, then one of these is non-zero, and we have a non-trivial linear combination adding up to 0. Is that possible? No, because these vectors are linearly independent, okay? So we deduce immediately that C0 cannot be 0. C0 is not equal to 0. Because otherwise, one of the CI's for 1 less than I less than or equal to K is non-zero. And we have C1 V1 plus C2 V2 plus dot, 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 plus CK VK equals the 0 vector. But what hypothesis do we have? We have that these guys are linearly independent. So the only solution to this equation is all of these things being equal to 0. Hence, it is impossible that C0 is equal to 0. So, and hence, we can simply write X equals minus C1 over C0 times V1 minus C2 over C0 times V2 minus dot, 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 minus CK over C0 times VK. So the whole point of the game was to show that we're not dividing by 0, okay? We want to solve for X as a linear combination, and so here's alpha 1, here's alpha 2, here's alpha k. Okay, so we've written X as a linear combination of those vectors. And we needed all of our hypotheses. We needed this set to be dependent, X dependent, and these guys independent. Dependent, we can write down a non-trivial solution to this equation, and then we figure out that this coefficient cannot be 0, so we can just isolate x and do simple algebra. Okay? And then I'll include the uniqueness part later. Okay. Leave myself some space for that. Okay, so we're about to finish chapter 2. Chapter 3, we do integration. We're going to compute the area under functions. That's what integrals are. And we're going to start with monomials. And we'll use Archimedes' approximation principle, just like the way we calculated for the triangle. Okay? When you did it for the triangle, that's x to power 1. We did sums of the integers to power 1. And we had a nice closed form solution for that, n times n plus 1 over 2. When we do a monomial of x to power k, we're going to need the sums of I equals 1 to n of the kth power of those integers. And lucky for us, has already computed this so that we don't have to, okay? Okay, so main thing, sums integers to power k. When we do our lower approximation for area and upper approximation for area, the thing that will pop out are these sums like that. Okay, so I'll move this down where it all fits on the page and shows. Okay, so the key thing is, okay, so we did this one. This is n times n plus 1 over 2. So it looks like n squared, when you multiply it out, plus n over 2. When you add up the square of the integers, okay, there's a beautiful thing, but it looks like n cubed over 3 plus n squared over 2 plus lower order terms. And that's what this is, would be n over 6, okay? 3 over 6, that's the 2 here. You add the cubic power, you get n to the 4th over 4. There's a beautiful pattern here. You add it up to power k, and you get n to the k over k, n to the k plus 1 over k plus 1, and then n to the k over 2. All of them are like that. They all have this same pattern. This big O, n minus 1, that's just a fancy way of saying, yes, there are other terms in there, but they're small compared to the others. We're looking at the dominant terms, the 6th power and the 5th power, for example, and everything else is 4, 3, 2, 1, 0, etc. And some of those may have 0 coefficients, but we just don't care. Okay? So the key thing is, when you add up the kth power, it's always n to the k plus 1 over k plus 1, and then the next thing has a coefficient of 1/2, and then there's a whole bunch of other little things. And that is going to give us really simple and amazing results for the area under monomials. Now, I don't know about you, but I did my calculus when it was really the hard way of doing calculus. I never realized that integral of x to the k going to x to the k plus 1 over k plus 1, it all just comes from adding up integers and powers, okay? That's where it comes from. Did they teach that in Math 116 here? No. Okay, so we're just going to try to do every once in a while, get down into the guts of calculus, what makes it work. So it's not just magic, okay? And adding up powers of integers is pretty elementary. Getting these beautiful formulas, that's really hard and stuff, but once again, it's been done for us. But this structure is what gives you the integral of a monomial goes to the next power divided by, etc. Okay. We're going to be quick here, most 5 or 10 minutes. Leave early. Okay, so this is, I keep saying this. We do proofs so that things that are intuitively obvious, we can separate them from what's really true. Some of it is just noise. So Georg Cantor in 1874 proved some really beautiful results that were completely rejected by the mathematical community. And they were so harsh to him that he had to be checked into a mental health care facility. They didn't call them such nice things back in the day, okay? Now, he was right, and the mathematical community was wrong. He was proven right about 15 years later. He was still alive, but sort of uninterested in being right at that time, okay? He was just trying to take care of himself. So what was the subject he was working on? And the reason I'm talking about this is just because I'm going to show you some things where you're going to make a guess about what's true, okay? And then we're going to see what the facts are. And if you want, you can read in the book how Cantor did it. We're not going to spend the time to do it this semester. But here's a concept from set theory. It's called cardinality. The cardinality of a set is just the number of elements in the set. Really complicated, okay? Got a fancy name. So if my set has our 3 favorite irrational numbers, Euler's number, square root of 2, and pi, its cardinality is 3. There's 3 elements, okay? Now, if you take the counting numbers, they don't end. So the cardinality has to be infinity, Everybody agree? This is not fake, it's true, okay? It's infinity. Now take the rational numbers, and we'll just use the positive rational numbers. There are at least as many rational numbers as there are integers. There's more of them, right? So that can't be smaller, it's still infinity. And then the real numbers, there's even more real numbers than there are rational numbers, or at least we think there are more of them. So that cardinality is infinity as well. So what Cantor asked is, are there more rational numbers than there are counting numbers? And are there more real numbers than there are rational numbers? Is it true that there are more? So what do you guys think? There's 3 infinities written down here. Is it possible that there's more than one kind of infinity? Okay, that's the big question. And in the 1870s, Cantor's thought process on that was totally rejected, okay, totally. Now, I want to know what your thought process is. Are there more rational numbers than there are integers, yes or no? So this means yes, and this means no. Okay, do I have any no's? One no, okay, because you've had EECS 203 recently, okay. And then real numbers. Are there more real numbers than there are rational numbers? This is yes, and this is no. So you guys believe that there's more real numbers than rational numbers, and the majority of the class, so the gang that was hassling Cantor, you would have been part of it. You'd have been there with your pitchforks and your torches trying to burn his house down, okay? Because you said, obviously there are more rational numbers than there are counting numbers. Okay, so Cantor proved that the rational numbers are in one-to-one correspondence with the integers. They're the same number. It's a really beautiful argument. It's called the Cantor diagonal argument. And so I invite you, it's given in chapter 1 of our book if you want to read it. Knowing that is not going to get you a patent. Just knowing that is not going to get you an extra grade when you take Rob 311 or something that depends on this course, okay? But it's still kind of intellectually interesting because it seems totally counterintuitive. Totally counterintuitive. And this is where proofs separate the intuitively obvious that there are more rational numbers than there are integers from the correct. So the infinities here, they are equal. And one way you can start thinking about this is, okay, let's think about the even numbers. 2, 3, 4, 5, 2, 3, 2, 4, 6, 8. Who do we appreciate? Okay, so even numbers. How many even numbers are there? Infinity, it goes on, okay. So, are there half as many even numbers as there are natural numbers? Seems like it. We only use half of them, and we've got the odd ones. We got 1, 3, 5, 7, okay? So we can write the natural numbers as the union, and there's no overlap, so there's disjoint of even numbers and odd numbers. But the even, pull out the 2, and you've got 2 times 1, 2, 3, 4, 5, and you're in one-to-one correspondence with the integers again, okay? So that's a simple argument showing that half of infinity can be infinity itself. They're one-to-one correspondent. You see that? Now, proving the rational numbers is much more complicated, but it's really fun. And I'll just give you the gist of it, and then we stop. I'm going to build a table that has every rational number repeated an infinite number of times. And what Cantor showed was that this table is in one-to-one correspondence with the natural numbers, okay? So I put 1, 2, 3, 4, 5 on the top, and then their ratios. So this is 1, that's 1. So I mean, every rational number is repeated here an infinite number of times, because if you have 2/3, that's the same as 4/6, which is the same as et cetera, okay? So every rational number appears an infinite number of times. So if this is in one-to-one correspondence with the integers, we can take a subset of it, and it is. And the way Cantor did it was, it's called the Cantor snake. Here's the first number, here's the second number, third number, fourth number, fifth number, sixth number, seventh number, eighth. And you give me any rational number, I can now assign a number to it by this Cantor's broken snake, okay? So it's called the Cantor diagonal argument because you're working on the reverse diagonals, just sort of like doing determinants. And so if this huge set is not bigger than the integers 1, 2, 3, 4, 5, the natural numbers, then the rational numbers are not bigger, okay, because they're a subset of this. So we'll stop there. We actually finishing 10 minutes early. That's great. I'm sure it's still dark out. There's no way we can get out early enough, but yeah, you can be totally right, and then everybody hates you because you are defying their expectations of how things should be. Life is hard. You're Bernoulli, and Euler gets the name your constant, and you're Cantor, and you're essentially driven insane. Monday, there's no class, right? Because that's MLK Day. We'll meet again on Wednesday of next week.